Let's go through one of the most common system design interview questions, which is to design a real-time collaborative doc editor, something like Google Docs, where multiple users can edit the same document at the same time and see each other's changes live. We are going to tackle this in 4 simple phases. So in the first phase, we'll gather the requirements and estimate the storage and everything that we need for this system. Then we'll get into high-level design and come up with all the components that we'll need to be able to design this at a high level. And after that, we'll move on to coming up with the database design and handling the most important part of this system, which is concurrency when multiple users are editing the same document. Let's start with the design requirements, which includes both functional and non-functional requirements. First of all, let's focus on the functional ones. So users should be able to create documents, edit them, and also delete these documents. Now, creating and deleting is just a CRUD operation in this type of system. Editing is where the complexity will be mostly. Also, multiple users should be able to edit the same document simultaneously and see each other's changes live. So these changes should be visible to all the editors in real time for the same document. And of course, documents should be persisted, meaning they should survive a page refresh. If a user typed something new in this document and then the page accidentally got refreshed, the changes should be persisted. Some clarifying questions that we can ask here if this is an interview setup. An important one is what kind of content are we storing, because it might be just a pure text, in which case we don't need to store a complex structure. But assuming it's Google Doc, we should be able to store rich text, meaning italics, bolds, and be able to apply styling to the text. This is important because based on that, we'll make the database choice later on. Also, who can edit these files, whether it's publicly accessible, like we can make it edit for everyone, as we have on Google Docs, or it's with invited users only. In this case, let's say the invited users can edit these only. And whether we provide offline support or not, which is a less important part in this system. So let's just say, no, we don't need to provide with offline support. So these are the core functional requirements. Now let's see what are the non-functional requirements that we need to support. First of all, let's start from the latency. So edits should appear to the other users who are working on this same document within 100 milliseconds. This number should tell us that HTTP polling, of course, won't work for this level of latency. So we need to go with a WebSocket option for providing the connection to the users. Then we have the availability. For this one, let's just go with a standard 99.9% of uptime. When it comes to durability, no data should be lost if a server crashes in the middle of the edit. So we should maintain this state locally on the client side as well, so that if the server didn't acknowledge the changes that we made as an edit, then we should be able to retry that edit with the server. And another important part is consistency, which means that all of the users should see the same document state eventually. For this part, some of the clarifying questions that we can ask to see what is the scale that we're dealing with here is how many registered users will we have. Let's say it's 10 million. This part specifically has less impact on the real-time design that we will do, but it helps us to do the overall scaling estimates. The important part is how many concurrent editors can we have in a single document. Let's just assume maximum 500 concurrent editors. And another important part is what's the maximum document size. Let's say it's up to 500 kilobytes. This part is important for 3 reasons. First of all, it gives us an idea on how we will edit pieces of this document and not the entire document on every request. Second is whether we will hit the limits of the database when storing this document content. And third, also for us to get an idea on how we will cache these documents. These are the core requirements of the Google Doc or a real-time doc collaboration tool. So based on these numbers, let's now do a back of the envelope or estimation of the storage, and then we'll get to the high-level design. Since we have 10 million users, we can either assume the active amount of users at peak, or we can just ask it to the interviewer if this was an interview setup. Let's just assume it's 1% of overall users that will be active at peak times, which will come down to 100,000 active users. We also need the average users that will be working on a document. We have the maximum number, which is 500, but we also need the average. Let's say it's 5 users. So this will come down to around 20,000 active documents that we'll be working with at peak time. Since 500 kilobytes is the maximum size we can expect, if we multiply that by the amount of active documents that we'll be dealing with at a given moment, it comes down to a maximum 10 gigabytes of active data, which fits in one Redis cluster. Worst case scenario is that if we are at the peak traffic and also each of these docs is at the peak concurrent editors, which is 500 editors per document, if we multiply that by the 20,000, it will come down to 10 million concurrent WebSocket connections that we'll need to handle. But this is the very worst case, and it's very unlikely that it will happen. But we always calculate for the worst case scenario. There isn't a specific amount on how many connections one WebSocket server handles. It also comes down to the data that you're transferring between the server and the client. But on average, let's just assume it's around 50,000 connections that we can handle in one server. That comes down to having 200 servers needed at the peak time, and we can set it up with auto scaling. So if it's not at peak time, then we can downscale the servers and just have the ones that are serving the traffic. Now that the requirements and estimates are clear, we can get into the high-level design and think about the general components we will need for this type of system. You have the client where the user is browsing this Google Doc and making edits. Of course, we mentioned that users should be able to create and delete documents, but that's just CRUD operations to the server to send a request to create a document or send a request to delete a document. So in this flow specifically, let's focus what happens if user opens an existing document and starts making edits. This is where we need to connect to the gateway with a WebSocket. The reason behind this is the collaborative requirement where two users should be able to update the same document and see each other's changes live. If you have two clients connecting to the backend and working on the same document, how are you gonna notify the first user that the second user made edits on that document? If you were to use HTTP, you could maybe send a server send event, but first of all, that won't match the latency requirements that we have, and it's not the ideal solution if both of them are working on the same document at the same time. That's why we go with WebSocket to have one persistent connection throughout the session. So this comes to the API gateway, first of all, to check the authentication, the rate limits, and then we proxy this same WebSocket connection to a WebSocket server, which handles the updates. This alone is not enough for us to provide with less than 100 milliseconds latency, because if we start reading from the database, it will easily take us more than this number. That's why we need to introduce a Redis cluster. So if two users or more are working on the same document, they connect to the same Redis cluster, and this Redis cluster can broadcast the edits across the WebSocket servers. And this also acts as a cache because it holds all the active documents in the memory of Redis, so we can read it directly from here instead of from the database, which is way faster than reading from the database itself. But we also need a persistent storage, of course. We can't go with the Redis cluster only, as this is not persistent. So for persisting these edits, we can have a separate service that talks to the database directly, something like document service. This is what validates the edits that are coming from the WebSocket server, persists them to some sort of database. We'll get to choose the database type soon. And it also validates the versions and edits and also manages the conflicts. So the flow is like this. Let's say you have user A and B who are connecting to different WebSocket servers. They don't have to connect to the same one to be able to work on the same document. So the first one connects to the server 1, the second one connects to the server 2. Let's say for now there are no conflicts, so user A just publishes an edit, they make a change in the document, and this gets published to the Redis PubSub. From here, we broadcast this change to the WebSocket server 2, and this is what forwards the edit to the user B, so that user B sees the edit that was made by this first user on their client. Now that's in case there are no conflicts and user A just edited something that user B didn't, so the user B just sees the updates from user A. But what if there are conflicts? To be able to think about this, it first makes sense to come up with a database, at least high-level design on what are the fields, how we will manage this, and then get to resolving the concurrency. First, let's define how the structure will look like, and then we'll get to choose what type of database or databases we will use in this situation. So, of course, the core of this system are the documents. We have documents with ID, with title, with content. This is the important part. Why we specified that it's a rich text document in the beginning is because we need to know how to store this. If it's a rich text document, it makes sense to store this in some sort of JSON format. So either it's JSON in a document database or it's JSONB in PostgreSQL. Both of these would work. You just need to know the pros and cons of each. So in case of PostgreSQL, it supports a JSONB column type natively, which means that you can store entire rich text content in a tree format. And why we store it in a tree format, let's say you have this text in Google document. So you have paragraph 1, then you have a new line, and you have paragraph 2. And here maybe one of the texts is bold, one of the texts is italic, and also with an underline. If you store this in a JSON format, you can also specify the type for each of these blocks of the text, and you can know on the front end if you need to render this part in bold or this part in italic and so on. Another option, you can use MongoDB for everything, for documents, collaborators, users, and so on. In this case, you have no schema friction. The trade-off is that you lose the relational integrity. For example, if we get to the rest of this schema, we also have collaborators and users, and the connection between users and collaborators is a foreign key, which you won't get in MongoDB if you go with a document-based database. And the third option is that you can actually split it. You can use PostgreSQL for the relationships between collaborators, users, and documents, and you can use MongoDB for storing the content. The downside in this case is that you create a distributed transaction problem. What if you have a transaction in SQL where the write to the document title and some other fields in collaborators succeeds, but then the content update fails in MongoDB? You need to start supporting distributed transactions, be able to revert it back, and this adds complexity, especially if you don't have a good reason to go with two databases. So each of the options has its pros and cons, and the core thing here is just to know the difference between these. I personally would go with PostgreSQL with JSONB field for the content, unless there is a specific requirement or reason to introduce a second database or to go with a document-based database only. And why PostgreSQL is the safe option in general is because you have other relationships also between documents and the collaborators, which links to the document ID. You have the collaborator IDs, and also you need to manage the permissions. Since in the requirements we discussed that this should be white-based, we need to be able to add permissions to the collaborators, whether they are an editor, a viewer, or just a commenter on the doc. We need to manage those permissions in this field. And this links back to the users table, where we have the user details like name, email, and so on. So rest of these document fields are just extra metadata that we need to maintain. Of course, also the owner ID to know who is the owner of this document. And an important part here is the version, which we'll see why in a bit. But for now, let's also see why we will send deltas to make these updates and not the full documents. So since we clarified that each document can be up to 500 kilobytes, if we assume 100 users are working on the same doc, or not even 100, like 10 users are working on the same doc, If they make one update, each of those, and let's assume there is no conflict, each of them is working on a different piece of the document, that will come down to 5 megabytes in case of 10 users or 15 megabytes in case of 100 users per second that we need to send and update in the database. So this way the network will get saturated very easily. Since we chose to go with the JSON format, this is how we can use and leverage that to update the deltas only. Let's say one of the users updates only 50 bytes in the document. We only send that piece of information to the backend with the type. Let's say this is inserting characters in between paragraphs. We give the position where this needs to be inserted, the text if it's just a text, and we also will provide the type of this if there are any, let's say, bolds, italics in between, and the version of the document that we also send along with every edit, and some more data about the edit, but in general that's how it looks like for updating a piece of this document. So in this case, if 100 users are typing, we only send 5 kilobytes per second for making this update in the backend. After having the database rough design, we can now think about the concurrency problem. In the first scenario, we just discussed if user A, let's say, updates the document and user B just sees those updates in case there are no conflicts. But what if we have the same document at version 4, let's say, and this is the text that we have inside. So user A deletes the word world from this text, and then user B adds this exclamation mark at the position 11 at the end of this text. So both of these changes arrive to the WebSocket servers at the same time, and now we have a conflict on the same paragraph, same block of text that two users are trying to modify. What we can do is each of these edits can include the document version. This is why we added this in the database. And based on this, if users B edit arrives with version 4, but the document is already at version 5, then the server rejects this and asks the client to refetch and retry the edit again. This is how it will work with optimistic locking. It will work decently, but it's not great user experience, of course, because if you made an edit and now the server is asking you to re-edit because there are issues, that's not ideal. But that's at least where we can start from as a simple solution. So let's say we have that user A, user B, both of these edited the document with version 4, sent the edits to their corresponding WebSocket server. The server applies the edit and updates the version of the document to B5. And then if this second user tried the edit later than the first one, then they still send the version 4 to be updated. And in the database, we will see that there is a version mismatch. They are trying to update the version 4, but version 5 already exists, which was updated by user A. So in this case, we reject them to the second user, asking them to refetch the latest document and return the document to the user, and then they can apply the edits to the version 5 document. After that, if there are no more conflicts, we apply that edit and change the document version to version 6. And now the version matches, so we apply the edit to the document. That's the first step, at least, on where we can start from, but there are actually techniques for managing these type of issues. The one we discussed is optimistic locking, where a conflict is detected based on the version of the document. So one of the edits is rejected, user must retry the same edits, and it gives the user a bit of bad user experience, right? Because they have to reapply the changes. Now, when it comes to these techniques specifically for system design interviews, you don't have to know them exactly. As long as you can at least reason about this with the first option, that's good enough. Of course, if you know any more than that, that's just a bonus point on top of it. So there are actually two more techniques that help us manage these conflicts better. One of them is operational transformation, which is the one that's used by Google. So in this case, both edits arrive to the server. Then server transforms the positions and both edits end up being applied. That's how if you change anything on Google Doc, you'll never see the server asking you to edit the same stuff again, because no data is lost with this type of transformation. For example, if we go back to that previous example, if user A inserts X at position 5 and user B deletes the position 3 from the same word simultaneously, after the second action of deleting the third position letter, the position 5 is shifted to 4. So in case of operational transformation, if one of the users, let's say, is editing this text, let's just say this client's text, and user A inserts X at the last position here, and user B deletes the fourth letter like E from this text. The way we manage it is after user B's delete operation, position 5 is shifted to position 4, and we adjust also user A's operation automatically, and this way both users' edits survive. Another technique that is used by Figma is called CRDT. It stands for conflict-free replicated data type. In this case, the data structure itself handles the merging, so each character gets a unique ID and a relationship to its neighbors instead of a position. This way, no central coordinator is needed. Of course, this is because Figma handles more complex relationships than in text in Google Docs, but these are, for example, two of the popular conflict resolution mechanisms in this type of system. Again, you don't have to know it exactly. You are not expected to talk about this in an interview, but knowing it is a bonus point over someone else who doesn't know this. If you found this helpful and would like to also learn the components that go into designing such systems like this one or any other system, then I recommend you watch this full course next, where I break down all the components that you need to know to be able to design systems like this and make the architectural decisions.